Today we will be looking at 8.4 graphing rational functions. So we're kind of getting into the meat and potatoes, if you will, of chapter 8. Up to this point, we've kind of explored how to multiply and divide rational functions, how to add and subtract rational functions. We're going to use some of those same strategies to help us come up and create the graphs of these rational functions. Okay. Again, keep in mind as we go through algebra 2, a lot of algebra 2 is going to be non-linear type graphs. So we're not graphing lines anymore. We're graphing more complex functions. All right. So this first page, you guys, I'm not going to spend a ton of time on the video talking about it, but there are specific aspects of these graphs we're going to look for. So vertical, horizontal, and oblique asymptotes, as well as identifying the domain and range of the function and the x and y intercepts. Okay, we already know how to find x and y intercepts of graphs. Okay, we've done that before. Vertical and horizontal asymptotes are going to be new. Okay, keep in mind we cannot divide by 0. All right, and then kind of the big thing for our horizontal asymptotes is going to be right here. Okay, and I'll just kind of quick explanation here. If the power is bigger on top, so if a of x is greater than b of x, so if the power is bigger on top, there is no horizontal asymptote. Okay, if the powers is bigger on the bottom, all right, meaning you have like x squared over x cubed, the power is bigger on the bottom, your horizontal asymptote is always going to be 0. Okay, if the powers are the same, you have some sort of, x cubed over x cubed, the asymptote is going to be the ratio of those polynomials leading coefficients. Okay, and I'll kind of go through each of those as we go to town here. But vertical asymptotes are related to holes on your graph, and I'll show you that in a second. Horizontal asymptotes, we need to be able to identify. Oblique asymptotes, and then obviously x and y intercept and domain and range. Oblique asymptotes and points of discontinuity. All right. The holes, point discontinuities, are going to be when factors cancel on the top and bottom. Okay. So keep in mind, holes are, I guess, it's probably easier to see in an example, but a hole is going to happen when you have a factor that cancels on the top and bottom. Oblique asymptotes arise when the power is larger on the top. And then after you simplify and factor, there's still more factors on the top than the bottom. Then there would be an oblique asymptote, okay? And we'll show you how to figure those out. And then actually how to find the oblique asymptote. We are going to have to do a little long division today, but just keep in mind it is pretty straightforward, okay? So I've kind of given you 3 examples here. So kind of the first example is going to be your basic like rational function, okay? And then the next 2 are going to be a little more complex, and we start introducing, on part B, we're going to start introducing an oblique asymptote and show you how to get that. Part C, it's going to be a graph with holes, okay? So keep in mind we're going to go through a bunch of strategies, and these should hopefully help you graph any situation. So I tried to pick some easy and more complex ones. All right, so we're going to start with the very first one. Okay, very first thing you want to do is factor. Okay, in this situation, I see that it is already factored. Okay, so then I can start picking things off. All right, typically what I like to do, sorry, x and y intercepted are on here as well. Okay. Oh, actually, I forgot. We took off the range. All we're concerned about is the domain. Okay. So after you factor, I like to identify the domain. Okay. So I'm looking at my denominator. I know I can't divide by 0. So in this case, I know that x can't be 0. Obviously, there's going to be more problems that are slightly more complex as we go through things. That's the first thing I'm going to look at. All right. At this point, the next thing I like to figure out is 0 a vertical asymptote or is it a hole? And that's kind of why I paired those together, you guys. All right. So your domain restrictions are either asymptotes or holes. You're never going to have 0 be an asymptote and a hole, if that makes sense. Okay. So looking here, I know that the factor x cubed did not cancel with anything on top, which leads me to believe that 0 is a asymptote. And since that's the only restriction and it's an asymptote, then my graph will not have any holes. Okay. I'm actually going to do this problem a little differently than I originally set out for. What I'm going to do is I'm going to figure out domain, vertical asymptotes, and holes of all three situations. Okay. So now we're going to go into this next one. Okay. Looking at this, it's going to factor into x minus 1, x squared plus 1x plus 1, because that's a difference of cubes. And then the bottom is x plus 2, x minus 2. Okay. So again, just like before, after we factor, we want to identify domain restrictions. In this case, I know that x can't be positive or negative 2. And actually, for the sake of things coming up, I'm going to write it like this. All right. So we have our two restrictions. We need to figure out, are those asymptotes or are they holes? Well, the question is, does the factor x plus 2 cancel or simplify with something on top? No. So negative 2 is going to be an asymptote. X minus 2 also does not cancel. So we have a vertical asymptote at positive 2. Since each of those domain restrictions are asymptotes and there's no other restrictions, this graph must not have any holes. Okay, and we'll show you what they look like in just a second. All right, this last one, it looks like we can factor our numerator by grouping. So I'm going to factor out an x squared. I'm going to be left with x plus 2. And then I have x squared minus 9, which is going to factor into x plus 3, x minus 3, and x plus 2. The denominator is a difference of squares. That's going to factor into x plus 3 and x minus 3. Okay. Again, look at our denominator for those restrictions. I know that x can't be negative 3. I know x can't be positive 3. Can't divide by 0. Okay. Now we need to identify, are those vertical asymptotes or are they holes? Well, if I look at the problem, x plus 3 is a factor on the top and bottom. That leads me to believe that I'm going to have a hole on my graph at negative 3. Okay. A hole is just an open circle. It's a break in your graph. All right. Looking at 3, my domain restriction, x minus 3 is a factor on top and bottom. So I know there's a hole at 3. Since in this case, both of our domain restrictions are holes, that leads me to believe there are no vertical asymptotes on my graph. All right. So now the question is, how do I get those y values in my hole? Well, it's actually really simple. So if you notice our function here, we factored everything, we simplified. What we do is we take these values and we plug them into our simplified function. So what's negative 3 plus 2? Negative 1. What's 3 plus 2? 5. So figuring out the y coordinates of those holes is super easy. Again, you want to plug those corresponding x values into the simplified function. All right. So that's the first step when I approach all of these rational functions. I want to factor, I want to figure out my domain restrictions, and then I want to figure out, are they a vertical asymptote or are they a hole? Okay. The next thing I like to address is the other asymptotes, the horizontal and oblique asymptotes. Okay. Remember, like we said before on the front, we want to look at the degree of the top, the degree of the bottom. So we have a degree of 1, degree of 3. Remember, when the degree is bigger on the bottom, you have a horizontal asymptote at 0. Okay. If you have a horizontal asymptote, there is not going to be an oblique one. Okay, let me say that again. If you have a horizontal asymptote, you will not have an oblique. All right, looking at the next situation. All right, the power is 3 over 2, or the degree of the top polynomial is 3, the degree of our denominator is 2. When the power is bigger on top, that's when we have no horizontal asymptote. In these situations, again, when the power is bigger on top, there could potentially be an oblique asymptote. Okay, or actually there is an oblique asymptote. All right, we didn't have holes in this graph, nothing canceled. So then the question is, how do we figure out my oblique asymptote? Well, what you do is the long, whoops, that's not a square root, sorry, that's supposed to be division, long division. X cubed minus 1 divided by x squared. So if you think back, we're going to wind up with a x cubed minus 4x, and then we subtract. All right, 0 minus a negative 4x is 4x minus 1. All right, I can't do any more division. That remainder, irrelevant. Okay, the only thing you're concerned about with your long division is the quotient, because whatever you get for the quotient, that is your oblique asymptote. Okay, so again, to recap this situation, the degree of our numerator was larger than the degree of our denominator. Our graph did not have holes, so the factors in our denominator did not cancel, which means there is an oblique asymptote, and I needed to do long division to figure out what the oblique asymptote is. The quotient is your oblique asymptote. The remainder is irrelevant, okay? And keep in mind, in these problems, our oblique asymptote should always be an equation of a line. So your equation will always be in the form y equals mx plus b in the end. All right? Looking at our third situation, again, we have a power in our numerator that's 3, power in our denominator that's 2. So it's really similar to the last situation. So you're like, oh, there's got to be an oblique asymptote. But when we simplified our function, the only thing left is this x plus 2. There is no division to do. There's no terms left in my denominator. Therefore, there is no oblique asymptote. All right. And as we said before, when the power is bigger on top, there is no horizontal asymptote. All right. So those are 3 different situations. The first one, obviously, where we have that horizontal asymptote. The second is where we used long division to come up with our oblique asymptote because the power is bigger on top. And then C, we have another situation where we have power is bigger on top, but the factors canceled, so there were holes and not an oblique asymptote. The last thing we want to figure out before we graph are the x and y intercepts. And again, remember, these are quite easy to determine. All right, and we're going to show you some strategies here. Remember, the x-intercept is where y is 0, and the y-intercept is where x is 0. Well, looking at this situation, remember, our domain, 0 is not an option. So there is no y-intercept in this case. The x-intercept, you guys, super easy because we have fractions, right? How does a fraction equal 0? Well, it only equals 0 if the top equals 0. So what value of x is going to make that 0? Negative 1. Again, super easy concept to kind of think about. All right. So again, looking here, we plug in 0. We're going to get 1/4 as our y-intercept. Again, the y-intercepts are pretty easy. The x-intercept is where we want to look at the top, okay? We want to set the top equal to 0 and solve. So I know I'm going to have an intercept when x is 1, all right? If you notice this next part, if I plug in like we're setting each portion equal to 0. This one is going to be complex if we plug it in. So we only have that one intercept. Again, the last situation, we want to plug in 0 for x and y. All right. So when I plug in 0 for x's to get my y-intercept, negative 18 over negative 9 is positive 2. And then again, figuring out our x-intercepts, we want to go to the top. Keep in mind, when there's holes, we want to go to the simplified polynomial or simplified function, okay? So we know that x plus 3, x minus 3, those factors simplified, those are holes, so they're not going to be intercepts on our graph, okay? They're holes in our graph. The only factor left in our numerator is x plus 2, which means I'm going to have an x-intercept at negative 2, all right? Once you've identified all this information, your domain, your vertical asymptotes, your holes, your horizontal asymptotes, your oblique asymptotes, your x and y intercepts, the graphs come together quite nicely, okay? So in this situation, we have horizontal asymptotes at 0. Again, use dashed lines to denote our asymptotes. We have an x-intercept at negative 1, 0. Please note that although this is on our x-intercept, that is a-okay, okay? Some of our graphs, as they get more complex, are actually going to go through an asymptote. That is a-okay. From here, you guys can just use your table feature on your calculator. Please make sure you use the original function and make sure to put the numerator and denominator in parentheses so your calculator calculates those values correctly. But you'll be able to figure out this is converging down to 0, and then up here you have another branch like that, okay? Again, you'll want to populate values in your table. Again, 2 per branch is what is encouraged. So you'd only need 1 on the left and 2 on the right in this situation, all right? Next one, we have vertical asymptotes at 2 and negative 2. So we're going to plot those in. We have x-intercepts at 1, 0, and 0, 1/4. Again, this is where we'd want to use our calculator to populate a table and even use it to help figure out the shape of our graph. As I graph on my calculator, you're going to see that middle one. It kind of goes up and down forever. Then I need 2 points to the left and 2 points to the right. So I would pick maybe 3 and 4 and negative 3 and negative 4. Get those values there. Forgot, this graph also has the oblique asymptote at y equals x. And then once you get the coordinates of 3 and 4 and negative 3 and negative 4, you'll be able to plot those other 2 branches in your graph. And again, those are going to be decimal values. Just approximate and plot from there. All right. The very last one, remember there's no oblique asymptotes in this situation, but there were 2 holes. Let me scroll back up so you can see. No oblique, no horizontal, no vertical asymptotes, but there's holes at negative 3, negative 1, and 3, 5. Negative 3, negative 1, and 3, 5. Okay, so literally those holes, we put a hole on our graph. From there, the question is, how else can I figure out what the graph looks like? Well, you can use your calculator or you can plot what's remaining. If you notice, the only thing remaining is x plus 2. Well, I know how to graph x plus 2. It's a line that starts at 2 and goes up 1 over 1. And if you notice, it coincides perfectly with your holes. It's the line x plus 2 that has 2 holes at negative 3 and positive 3. All right. So again, Given up here, kind of the rundown of things you want to factor, then I would go into domain, vertical asymptotes, and holes. That's kind of the first set of information. Then figure out the other asymptote situation. Is there a horizontal or oblique asymptote? And then finally, figure out your intercepts. At that point, you can go to your calculator, grab any remaining points from your calculator to help you graph. Use the picture to make a somewhat accurate graph. What I don't want to see, you guys, all right, if this is, if I'm copying this graph here, I don't want to see this, okay? Like chicken scratch, garbage. This is honors. Actually get 2 points per branch. Write those down. Use your calculator to help, but put a little more than 10 seconds of effort into your graphs. It would be appreciated. The assignment down there, again, keep in mind, it's a few problems out of your textbook in the worksheet as well. If you do have questions, please let me know. Again, the big protocol through everything is factor first, figure out domain, vertical asymptotes, and holes, figure out horizontal and oblique asymptotes, figure out your X and Y intercepts. That's about 75% of the information you need to graph, and go to your calculator, grab any remaining points, and help use your calculator to create the shapes of those graphs. If you have questions, please reach out. Otherwise, best of luck on 8-4 today. I hope everything goes well.